We have focused so far on situations where we have a multi-category response and the corresponding categories for that variable do not have any particular kind of ordering with them. So for example, I cannot say category 2 is greater than category 1, category 3 is greater than category 2, and so on. I can't say that. But there are situations where we have a multi-category response and the categories do have a natural ordering to them. So that, let's say, category 1 is less than category 2 is less than all the way up to category capital J. This can happen, for example, when one has a Likert scale as a unit of measurement for your response variable, where you might have, let's say, categories strongly disagree, disagree, neutral, agree, and strongly agree. Now, when one does have ordered categories, one wants to, of course, then take that into account. And that can lead to, let's say, a better data analysis. You can maybe make stronger conclusions about your results than if you did not. And so the purpose of this section then is to talk about how can one take into account then these ordered categories in our response. And the number one way to think about how we can do that is now we're going to be focusing on modeling the cumulative probability for our response variable. So we're going to look at the probability y is less than or equal to j. So in other words, if I were to go back to the Likert scale situation, the probability that y is less than or equal to 1 would be pi 1, and that would correspond to the probability of disagreeing, strongly disagree. But I could also have the probability y is less than or equal to 2. That would be pi 1 plus pi 2. So the probability that you are that one responds with disagree or less. And since we have that ordering now, it makes sense to look at those categories in that way. And so what we're going to do is set up a model now for these cumulative probabilities in much the same way as what we did with the logistic regression model. So now we're going to model the logit of a cumulative probability. So in other words, we're going to have the log of the odds of our cumulative probability at category J. You could rewrite this as the log of the probability you are J or less, the probability that you are J plus 1 or more in terms of the categories. So again, what we're doing is going to model now the log odds of a particular, let me say that again. We're going to model a log odds with respect to these cumulative probabilities. There are a few different models that can do that. We're going to focus on the one that is most often used called the proportional odds regression model. I'll explain why proportional is in that name shortly, but you can see why odds, of course, is in there. And let's consider a simple setting where we only have one explanatory variable, and we have then the logit of the cumulative probability is equal to beta sub j0, just like what we saw with a multinomial regression model, plus beta 1 times x. Notice you do not have a second subscript on that beta like what we did with the multinomial regression model. We'll talk about that more shortly too. And notice how this model is defined. For j equal 1 up to capital J minus 1. Well, where is that capital J? Why don't I go up there? Well, because we know what the probability y is less than or equal to j, capital J, and that is, it's simply 1, because that's the highest of these categories. Okay. Now, similar to what we saw with logistic regression, one could rewrite this expression then so that I only have the probability on the left side, but now this is a cumulative probability. And on the right side, I have the exponential function evaluated at beta sub j0 plus beta 1 times x, all that divided by 1 plus the exponential function evaluated at beta sub j0 plus beta 1 times x. Okay, so where does this proportional name come into play here? Well, I could rewrite my model up here as follows. The probability that j, probability that y is less than or equal to little j over 1 minus the probability y is less than or equal to little j, my cumulative odds, you could say, is equal to the exponential function evaluated at beta j0 plus beta 1 times x. I could rewrite that further as this. The exponential function evaluated at beta j0 times the exponential function evaluated at beta 1 times x, just using properties of items up in an exponent. So let's take a closer look then at this expression. Notice that as j changes here, the odds only change because of this part right here, not because of our explanatory variable itself. And so that's where the proportionality or proportional part of the name comes into play. I want to interpret my model relative to what x is, and I will be using odds ratios to do that. But if we look at just in terms of this odds, then we can see for a fixed x, this essentially then changes what the odds is. So it makes then the proportional part. For a particular value here, I can multiply it by the exponential function evaluated at beta 1 times x, always. Now, also because of we're working with these cumulative probabilities, and that the probability y is less than or equal to 1 would have to be less than the probability y is less than or equal to 2. It would have to be less than or equal to the probability y is less than or equal to 3, and so on. Because of that, and because of our model structure, since those coefficients on x do not change at all, we just have like a beta 1. That means then that these betas have to be ordered in this particular way. Because for j equal 1, I'm going to have a smaller cumulative probability than I have for j equal 2, than I have for j equal 3, and so on. And so the way that I continually to increase that cumulative probability, these betas then have to increase as well. Now, these proportional odds regression models are part of, you could say, a little bit of a larger family called cumulative probability regression models, where the focus is on modeling cumulative probabilities rather than just directly the probabilities themselves, like what we've always seen before. And so there are cumulative probability regression models that allow for a subscript j to be in there with that beta 1. We will talk about those later on in the corresponding chapter here. They can have some problems with them, so that's why I'm going to delay talking about them until later. Now, what happens if you have more than one explanatory variable? But, well, as you might expect, you just add the corresponding beta and x terms to your model. Again, remember, this is only up to capital J minus 1. Well, what is then also pi sub little j here in the context of our regression model? We took some time to talk about that for a multinomial regression model before. Here's how you can do this for a proportional odds regression model. Well, pi sub j, well, what is that? Well, of course, it's just the probability that y is equal to j. So we could rewrite this, though, in terms of cumulative probabilities. The probability y is less than or equal to j minus the probability y is less than or equal to j minus 1. Then this just gives us this one case where y is equal to j. Well, what are these cumulative probabilities? Well, go back to your model. Just from what we saw before with our model, and let's just go back there just to make sure you see that. Just go back to your model and write it out in terms of if you're with category J or category J minus 1. And so that's how you can find pi sub little j. But note that this is for 2 all the way up to capital J minus 1. So then what is for j equal 1? Well, that means pi sub 1, or probability that y is equal to 1. Write it out just like I did here. Probability y is less than or equal to 1 minus the probability y is less than or equal to 0. Well, we don't have a category 0. We can't be less than that. So that probability has to be 0. And so you're just left with the probability y is less than or equal to 1. And here's where we are. What about for category capital J? So pi sub capital J is equal to the probability y is equal to capital J. Or in other words, write it out in terms of cumulative probabilities. Probability y is less than or equal to capital J minus the probability y is less than or equal to capital J minus 1. Well, that probability is equal to 1 because you can't be higher than category J, capital J. And so I have a 1 there, and then I can go back to my original model statement to find then what the probability y is less than or equal to J minus 1. Let's take a look at a plot of the model. So for this particular situation, I'm going to let beta 1 be equal to 2. So I have a slope of 2, you could say. I'm going to have just one explanatory variable. And I'm going to have capital J equal 4 different categories that are ordered, where I need to define beta 1, 0, beta 2, 0, and beta 3, 0. Notice how I have them equally spaced there. Through using the curve function in our expressions for our model that we just saw, make sure you are understanding how to use the curve function for this purpose, I can construct these following plots. So on the left side here, let me make this a little bit bigger too. On the left side here, I have x1 on the y-axis. I have this cumulative probability on the I have x1 on the x-axis. I have the cumulative probability on my y-axis. And then I go ahead and draw the model out so that the probability that y is less than or equal to 3 is represented by the blue dotted line, and then the probability y is less than or equal to 1 is represented by the black line there. And so we can see a similar shape that appears as a function of x. Why is that? Well, remember, for each category, we have the same slope. We have that beta 1 is equal to 2. That's why we see the same shape. And then the differences between these three lines there, that corresponds to that y-intercept term, that beta j0, you could say. I shouldn't call it a y-intercept term, just call it the intercept term of our regression model. Now we could also look at the same kind of plot, but now instead of having cumulative probability, suppose we have then just the probability y is equal to little j as a function of x. And this is what we get here. So notice here a particular ordering that we have. That notice for category 4 we are the highest here. Then for category 3, 2, and 1. That's going to be very important coming up when we look at this model and further understand what this model means. So how do we estimate the model? How do we perform inferences associated with this model? Well, we use maximum likelihood estimation again. There are two main functions in R that people use to estimate these particular models. The first function is the POLR function that exists in the MASS package. MASS stands for Modern Applied Statistics with S. This is a package that has been around for a long time, and because of that, the POLR function is the most used for these proportional odds regression models. This MASS package comes automatically installed in R with the default installation. You still will need to say library MASS before you use this particular function, so you can tell R, hey, I want to grab functions out of this package. The second function that can be used to estimate this kind of a model is called VGLM. We saw that with the multinomial regression model. It comes in the VGAM package. Here are some comments about these functions. Now, the actual model that the POLR function actually estimates is slightly different from the model that I presented. And I'll explain how we can convert it to the model that I presented shortly. Also, I should mention what POLR stands for. Sorry, I didn't do that before. It stands for Proportional Odds Logistic Regression. So they put the extra L on there because we saw the relationships with logistic regression before. Now, with this particular package, we can use the conf function to do profile likelihood ratio intervals for our regression parameters, but only for essentially one regression parameter at a time, unfortunately. We cannot use it for more complicated expressions amongst our regression parameters, and unfortunately the MC profile package does not work with this. So whenever we have a more complicated expression, you can imagine corresponding to what we saw with the logistic regression, you might have some kind of complicated odds ratio that involves multiple regression parameters. Whenever that occurs, the easiest way to go about finding then the corresponding confidence interval is to use the EM means package, but you end up with walled confidence intervals in the end. So with respect to VGLM, here's exactly what I said before regarding that when we were talking about multinomial regression models. This function is very useful. It can fit a number of different models associated with multi-category responses. Unfortunately, there are some aspects to it that prevent me from making this particular function recommended overall to estimate these models. Now, for both functions, it's important to have the levels of your categorical response variable ordered in the correct way. So one of the first things you should do is use the levels function with your response variable to look at what the levels, how the levels are ordered. And if you need to, use the factor function to reorder the levels corresponding to the actual ordering of those levels. You can get an estimated covariance matrix using similar methods as what we've seen before, because we're using maximum likelihood estimation. The vcov function can be very useful for this. And lastly, I am going to focus on using the POLR function here. If you want to know more about the VGLM function, I have some code in my program that shows how to actually use it in this particular setting. Now, before we actually look at how to estimate these models in R, there is something else I need to say, and that is with respect to various hypotheses that we might be interested in testing. Suppose we have the following model, logit of the probability that y is less than or equal to j is equal to beta j0 plus beta 1 times x1. Suppose I want to look at this beta 1 parameter to determine, to evaluate the importance of x1 in our model. And the way I would do that is similar to what we've seen again before, is do a hypothesis test for beta 1 is equal to 0 or not. Now, we see that if the null hypothesis is true, then that means that x doesn't have an effect on the response. In a contingency table setting like this, let's say maybe we had an indicator variable where we had two rows, we can say that x is independent of y. Now, the alternative hypothesis, though, this is a little bit different from what we've seen before with a multinomial regression model. If the alternative hypothesis is true, then it says the ordering of the log odds comparing these cumulative probabilities holds. But it holds in the manner that we've specified with our model. So our model does have some restrictions. We've talked about that. For example, how those beta j0s have to have a certain ordering. Also, how we have this ordering amongst our cumulative probabilities. So we have some restrictions in comparison to what we would have seen with a multinomial regression model. So in a very similar setting, if I wanted to evaluate the importance of our x explanatory variable in that setting, we would have then the following hypotheses where we set all the corresponding betas associated with the x variable. We would set them all equal to 0. I've ended up writing this out in terms of like a contingency table structure, even though I didn't have to, in terms of how we define the model then. The alternative hypothesis, of course, at least one of these beta j's are not equal to 0. Now, in this particular setting, if the null hypothesis is essentially equivalent to what we had with a proportional odds regression model, but the alternative hypothesis is not equivalent. This alternative hypothesis doesn't put any kind of ordering amongst our corresponding categories, thus the cumulative probabilities. And so, to some respect then, I should say to some respect, it is, this alternative hypothesis is more general. It allows you to have more flexibility than for what kind of dependence that one could actually have between your X variable and your response. Now you might think, well, that is actually good because you have less constraints. It's good in that respect, yes, but it actually may not be good though, because it can lead to a model that is less efficient than when the proportional odds assumptions are satisfied. Now these proportional odds assumptions that we have with our model, they're assumptions, but they are reasonable assumptions. We would expect, we have these cumulative probabilities associated with our model, and if you do indeed have category 2 greater than 1, 3 greater than 2, and so on, well, that seems reasonable. And since we have that restriction there, what that can end up doing is actually something that's good, and that is you can have more power for your hypothesis test when you test hypotheses like we just saw here. We will actually see an example of that coming up in another set of notes where we did essentially have more power, and it actually led to a different conclusion about our data. Okay, so let's go ahead and go back to the weak kernel data for now, and we're going to look at how we can apply the proportional odds regression model in that particular setting. First, we need to define an ordering amongst our kernel categories. Now, as I defined originally, healthy is better than scab or sprout. We want healthy kernels. So that makes sense to put that as, let's say, category J, capital J. But then we need to decide, well, what about an ordering for scab and sprout? Well, I'm not an expert in grain science, but I think it seems reasonable to think that sprout would be preferred over scab. Why would I want a disease kernel? That seems to be the less desirable situation. So because of that, I'm going to use then this ordering here. And also another reason why I decided to actually even use this kind of a data set with a proportional odds regression model is because in an educational setting such as this helps us compare results from a proportional odds regression model to a multinomial regression model. So let's take a look at how we can do this. I'm going to jump on over here to 10. So the first thing that I need to do is I need to look at the levels, how the levels are ordered for our type variable. This corresponds to the kernel types. And we see that they are actually not ordered the way we want. We want healthy, for example, to be that last category. We want scab, sprout, healthy. So to reorder the levels to how we want it so that R can take advantage of this ordering, we can use the factor function. So we say factor X equal, here's where my data is, the type variable of wheat, and then this is where I put in the new ordering for the categories. I'm going to put the results into a new column of my wheat data frame. I'm going to call that column type.order, and then we'll take a look at it and look at the levels. Okay, so notice type and type.order look exactly the same, but R recognizes the ordering of the levels in the correct way now for type.order. Okay, let me come back over here to Word. The model that I would like to estimate is this one here, where I'm modeling the logit of the cumulative probability. I have the intercept terms, plus here are the linear combination of my regression parameters with my explanatory variables. So for example, x1 is going to be moisture, x1 is going to be the class, soft red winter wheat or hard red winter wheat. x6 is going to be the moisture content of the kernel. To actually estimate the model in R, I say, first of all, I want to use the mass package, and then I'm going to estimate my model, put the results into mod.fit.org for the lack of a better name, estimate the model using the POLR function, and then I write out formula equal, Here's my new response variable, tilde. I put in my explanatory variables. I put in my data, and then while this is the default, I just put it here just for emphasis, method equal logistic, because we are kind of doing like a logistic regression kind of model is what we saw since we're modeling the log odds. Again, this is the default. You don't actually need to do that. Then I say, let's summarize the results, and here's what we get. We get some output that looks somewhat similar to what we've seen before. So for example, we have, I guess a difference is that notice we have the intercept terms separated from the other estimates of the regression parameters. The reason being is because we have multiple intercept terms. So for example, here is beta hat 10, here is beta hat 20. Notice we have some standard errors there. So here's the estimated square root of the estimated variance of beta hat 10. Okay. Now we also have a coefficients table, and what's actually displayed there is slightly different from what we want. What this function is actually estimating is this model, where what I'm highlighting here is what's different than from how I actually defined the model before. So in other words, rather than estimating, let's say, beta sub r for the rth explanatory variable, is actually estimating a negative version of it, what I call this eta instead. And so because of that, whenever I want to state my proportional odds regression model, when I see the estimated value here, I need to put a negative out in front of it. So in terms of our model, I have negative 0.17 times the soft red winter wheat indicator variable. Also, let's take a look at moisture. Notice I have a negative out in front of it. So if I put a negative out in front of negative 0.0392, I get a positive. And so notice how I have a positive 0.04 times moisture. Make sure that you always change those signs. And whenever you have to do, if you're taking my course, wherever you have to do some kind of graded item. This is an easy place to lose points on like a test. So make sure you always change those signs. And just for emphasis, let me tell you, you don't need to change the signs on those. Those are the correct beta hats. That's why I labeled those to begin with. So remember which of those estimated values you need to put a negative out in front on. So if I were to state my model, here's how I would state it. I do need to state separately the corresponding beta hats since I have more than one of them. Now in the output, you're going to see some t values. All that represents, this 0.4434 is 0.17 divided by 0.39. This gives us a walled test statistic to test whether or not the corresponding beta is equal to 0 or not. They don't, for some reason, put p-values there. I'm not for sure why. Even though it says t value, this is still a walled test statistic. So we would want to use a standard normal distribution approximation with the test statistic. In the end, it's preferable to use a likelihood ratio test because it's going to work out better with a likelihood ratio test. These are, again, similar to what we've seen before. Let's say the stated type 1 error rate will be closer to the actual type 1 error rate when you use a likelihood ratio test. So to do likelihood ratio tests in this kind of a setting, or similar setting, we've used like the little ANOVA function, we used the capital ANOVA function. Here's an example of how to use the capital ANOVA function, and I use it similar to what we've done before. Notice where we have the low p-values for density and weight. So we do have sufficient evidence that density and weight is important relative to these response categories. We have marginal evidence of importance for hardness. What about getting the pi hats? I might want, what's the probability a particular kernel is scab? What's the probability it's sprout? What's the probability it's healthy? Again, use your knowledge based upon what we've seen in the past to think about, well, how would I actually go about getting that? You might be wondering, well, is there a predict function? Yeah. So we use predict object equal, mod.fit.org. What kind of predictions do I want? I want to estimate those probabilities for each response category. So for example, for the first kernel, here is, let's say, pi hat sub healthy. I'm going to put the actual label there rather than 1, 2, or 3, just to make sure that there's no confusion in terms of the ordering that we have. And so we see the estimated probability of being healthy is 0.69 for kernels with those corresponding explanatory variable values. Sprout's 0.27, scab is 0.04 about. And so if I had to, let's say, choose a particular classification for this particular kernel, I would choose healthy because it has the highest probability associated with it. If you wanted to do that automatically, change the type argument to class. Here's the actual corresponding, you could say, by hand calculations to do these pi hat calculations. Make sure, if you're in my course, make sure you can actually do that. So that's why I give you an example with healthy. You'll see other examples in my program as well. Now, what about confidence intervals associated with these pi sub j values? Well, it's similar to what we saw with the multinomial regression function or multinomial regression model. Unfortunately, our packages that we can use to estimate this model do not provide us a way to find a confidence interval for pi sub j. So what we can do is go back to EM means and essentially use a very similar set of code now for this purpose here. So I say library package equal EM means to get the functions ready to go. And I say EM means object equal, here's my model fit from the POLR function. For my specs argument, again, I need to put in the actual response variable here. Remember how that's a little bit different from what we saw for a logist regression model. What values do I want to come up, what values do I want to estimate pi for in terms of the explanatory variable values? Let's just make things simple. Let's assume that we just use exactly the same values for the first kernel. I could have used different values if I wanted to. So I specify this with the at argument and then mode equal probability, meaning I want these pi's. So what we have here then in the output when I use the summary function, 95% intervals, we have the same pi hats that we saw before. So here's pi hat sub healthy. And now here is the corresponding confidence intervals. So pi sub healthy is somewhere between 0.85 and 0.53 approximately. Okay. Now let's try to visualize what our model is saying now. Since I have more than one explanatory variable, that's more difficult to do. So similar to what I did with a multinomial regression model, I'm going to look at a case where we only have density as my explanatory variable of interest. I re-estimate the model. This is what I get for my estimated model. And then I plot then the corresponding probabilities. Please take a look at my code. So I plot the probabilities as a function of density. So here's density. My estimated probability of having a particular category of a kernel is on the y-axis. Now in this plot, I have, you could say, two sets of lines for each color. The thicker lines correspond to our proportional odds regression model. The thinner lines correspond to the multinomial regression model that we looked at previously for this exact same setting. And so what we see here is that we have some very similar results to what we had with the multinomial regression model. But a key is that we're estimating much fewer parameters associated with this model. If one wanted to come up even with like a classification scheme, for should this be scab, should this be sprout, should this be healthy for a particular kernel, by looking at this particular plot and seeing where the highest probabilities are located. And again, compare this to what we saw with that parallel coordinate plot earlier. Okay, so this gives you an introduction to these proportional odds regression models.